once again we are back together. Right, and today we're going to be discussing energy and chemical change. So if you haven't subscribed, please just make sure you are part of this family. And of course, if you have some questions or having challenges with maths and science, you can always get in touch with us. All the information that you need will be on the description of this video. All right, now let's get right into our lesson. So first of all, let's talk about energy and chemical change. So firstly, right, whenever we've got a chemical reaction that takes place, now let's take hypothetically the following reaction, right? So we've got A2 plus B2 giving us, let's just say, 2AB, right? Now, there are two processes that must actually take place, right? The first process is that we must be breaking bonds, right? So we're going to be breaking bonds on this side. So bond breaking, okay, on the one hand, right? But on the other hand, we must be forming new bonds, right? That's the process, that's the chemical process, right? So here we are forming bonds. So this is the process of bond formation, right? So forming bonds over here. Now, this process either absorbs or in this case, uses up energy, right? So uses up energy, or in this case, it actually releases energy. So the process of bond breaking, or the breaking of bonds, right, is a process that requires energy. So here, energy is actually absorbed, right? So this guy will actually absorb energy in order for us to actually break those bonds, right? But now the process of bond formation, right? Once bonds are formed, actually energy is released. So we know this guy will actually give us energy, right? Now, I'm sure some of you know the law of conservation of energy, right? It says in an isolated system, right, energy cannot be created or destroyed, but it is actually transferred from one form to another, right? So we know that we are absorbing energy over here. We are releasing energy on the other, when we are forming bonds, right? Now let's talk a little bit more about this, right? So now there are two types of reactions that actually take place. And we're going to, at a later stage, talk about, the energy profile of a reaction, right? Now, in this case, when we absorb more energy, right? So think about it. So initially we are absorbing more energy than we are going to release, right? So in this case, we know that once bonds are formed, we're going to release energy. So if we are absorbing more than we are releasing, so I'm going to just designate A as absorption, and in this case, R for releasing. If we are absorbing more than we are releasing, then it means that the net energy, okay, so the net amount of energy that we will actually have in this case is actually energy that is absorbed, right? So as a result, we call this an endothermic reaction. So in this case, remember, we're still going through a process of having energy that is absorbed and energy that's released. However, if we've got more energy that is absorbed, in this case, we know that our net energy profile is such that it is endothermic, right? And I'm going to talk about this a little bit more as we go through the questions, right? Now, of course, we can have another process where there's very little energy that is required, right? So very little energy is absorbed during the process of, breaking of bonds, but we find that we've got more energy that is released. So we absorb less and we release more energy. So which means that the net amount of energy, right, that we get in this profile is actually energy that is released, right? So as a result, we call this an exothermic reaction, right? So it doesn't mean that when a reaction is exothermic, there was no energy that is absorbed, but it simply means that there was more that was released than one that was absorbed, right? So what we are going to now look at is what we call an energy profile. So we actually use a graph for this, right? The energy profile of a reaction. Now, before we talk about an energy profile, let me make just two examples, right? So for instance, if I take calcium carbonate, right, and we are going to actually take it through a process of decomposition, right? So what it forms is calcium oxide, and it also forms carbon dioxide, right? So you burn calcium carbonate, right? In order for this reaction to take place, what happens is that it requires quite an amount, a significant amount of energy in order for you to actually get this reaction going, right? So there is more energy that is required to be absorbed to break down the calcium carbonate, right? And there's very little energy that is actually released in the process. So in actual fact, we say that this reaction is an endothermic reaction. So this would be an endothermic reaction. On the other hand, ladies and gents, whenever a car has to move, right? We know that cars use fuel in order to move, right? So if you're taking petroleum, for instance, which is C8H18, right, and you actually, right, the process is that it burns in the presence of oxygen, excess oxygen. And what does it form? It forms carbon dioxide, right, plus H2O. But in this case, what happens is that for a car to move, it means that it must release a whole lot of this energy so that it drives the crank of the engine, right? So as a result, there's more energy that is released than one which is absorbed, right? So I want you to note, so as a result, we say that this is an exothermic reaction, okay? So what I'm going to do, ladies and gents, is that I'm going to show you a graph that we call the energy profile, right? And you're going to see this more in graphical form, and I'm going to explain some of the concepts that we use in this section. Right, now, let's talk about endothermic reaction, right? So the energy profile, firstly, what I want you to realize here is that when we draw the energy profile, we draw the potential energy of the, either the reactants or the products, right, against the progress of the reaction, or what we call the reaction coordinates, right? So sometimes we'll use the word reaction coordinates, but also please do remember that we can also call this the progress of the reaction. Right, now let's talk about the different parts that make up all of this. Right, number one, we know that on the reactant side, there is what we call the potential energy of the reactants, right? Now, this is the energy that is contained, right, within the intramolecular forces of the bonds, right? So the reactants themselves. Now, in this case, we spoke about A2 and B2. So both of them have got their own energy, right? Now, what do we need to do? We need to now increase, right? In order for this reaction to take place, what do we need to do? We need to now increase, all right? We're going to absorb energy. We need to put in energy for this reaction to take place. Now, guys, I want you to remember, and I've drawn this in yellow. We call this the activation energy of our forward reaction. Remember, we had A2 plus B2, which was giving us, all right, 2AB, right? So which means in order for A2 and B2 to break the bonds, in this case, what we need is activation energy. Now, guys, in yellow there, you can see we start from the reactants, from the energy of the reactants, all the way to what we call the activated complex. And I'm going to actually explain this concept of the activated complex a little bit more. Right. And then in blue, what I have there is that if I wanted to reverse the process, right? If I wanted to now break the bonds of my reactants, of my products rather, and form reactants again, right? Look at this. There's very little energy that is required to get to that point, in this case, that we call the activated complex. So this would be the activation energy. Let me just write it in blue there. This is the activation energy for the reverse reaction. Now, please, you need to remember this, right? So in yellow, we had the activation energy for the forward reaction, right? And I'm going to actually show you how to calculate this a little bit more. Now, ladies and gents, you remember we spoke about the net energy, right? Okay, so this net energy actually has a name, and that name, we call it the enthalpy. Okay, so we call it the enthalpy of the reaction. All right, or sometimes called the heat of the reaction. So the net energy, we call that the enthalpy change, or we call it the heat of the reaction. How do we get this energy? Well, look at this. The products also have got their own energy, right? Once they have formed, or rather formed those bonds, in this case, we now have the energy of the products. So the difference between the products, the energy of the products, right? The potential energy of the products minus the potential energy of the reactants, we call this the enthalpy change, right? So how we're going to calculate the enthalpy change, let me write that in green since it's indicated there in green, right? So we always say delta H, right? We use the energy of the products minus the energy of the reactants. Okay, right. So I want you to note, in this particular case, the energy of the products is much greater than the energy of the reactants. So what am I expecting? That delta H will actually be a positive value. It will be greater than 0, right? So note, if I want to calculate delta H, it will be from the products minus the energy of the reactants, and we've indicated it there. Guys, it would be actually very important for you to know what is happening on this graph. Okay, right. Now, let me give you just a heads up, right? So when you look at the energy profile, you must be able to tell whether it is an endothermic reaction or an exothermic reaction. As I said to you, so if the energy of the products, the potential energy of the products is greater than the energy, the potential energy of the reactants, then in that case, it would be an endothermic reaction. So look at what happened. We had more energy that is absorbed and little energy that is released. So in the process of bond formation, we released energy, but there is less energy that is released, but there is more that is absorbed. And as a result, we say that the net energy, in this case, the enthalpy change or the heat, will actually be positive. It is an endothermic reaction. All right, now, before I talk about the activated complex, let's talk about the exothermic reaction, right? Exactly the same graph that we've got there. However, in this case, we've got potential energy. By the way, just for you to note, remember that potential energy is measured in kilojoules per mole. Okay, so please don't be alarmed. Sometimes they don't put per mole, they just say kilojoules. But we know that it is energy And so it should be measured in joules. Okay, right. Now, look at this. The energy of the reactants. So the reactants have got a high amount of potential energy. And so they require very little activation energy, right? To get to that point, the activated complex. So they absorb very little energy until they get to the activated energy, the activated complex, right? And so what happens? We actually release even more energy in this case. So we've got more energy that is released than what is actually absorbed, right? During the process of bond formation. And so as a result, the products have got a lower amount of energy than the reactants. Okay, so as a result, what do we note? This is an exothermic reaction, right? So I want you to note, if we were going to calculate delta H for this energy profile, we know that delta H would be the energy of the products minus the energy of the reactants. But because the products have got less energy than the reactants, what we will then find is that delta H is less than 0. Okay, remember when you subtract something bigger from something smaller, so in this case we end up with a number that is negative. Okay, so delta H on our graph, this is where we would actually see our value for delta H. Right, I hope this is clear, ladies and gents. Right, now before I actually continue to the examples, let's talk about this activated complex. What's actually happening? Now, you remember when we spoke about the process of bond breaking and the process of bond formation, right? We said, first of all, we know that we're going to have two things that happen, right? So remember, when we talk about the energy profile, right, we've got the bond energy of the reactants, we've got the bond energy of the products, right? So now what happens is that we now put in an amount of energy in order for us to break the bonds, right? I want you to note, guys, what happens. This is the complex stage where in this case we are actually going through the process of the bonds are separating and the new ones are forming. Yes, I mean, think about it. We would say that it is complicated, right? So we are neither here nor there, right? We are still at the point where some of the bonds are breaking and we are in the process of forming new ones. And we say that this is called the activated complex, right? Now, this is what our energy profiles look like, right? And there are all sorts of things that we are now going to play around with, right? And please, I want you to remember that in order for this reaction to take place, there are collisions that must take place. So during that process, you're going to learn about this more in metric, right? Where we talk about the process of collisions taking place. Right, now let's take an example and see how to apply this in practice. Have a look at this question, right? So they say to us, we've got a barium hydroxide solution, right, that reacts with nitric acid solution, right, according to the following reaction. So they give us the reaction there, and they say the potential energy below, the potential energy graph rather below, shows the change in potential energy for this reaction. Right, I'm sure you can already tell, okay, what type of a reaction this is. Right, firstly, what are we going to note? We do note that the potential energy of our reactants is actually greater than the ones for our products. So remember, we've got reactants over here, okay, and we've got products over there, right? Now, what do we note? It means that our potential energy for the products are less than that of our reactants, right? So what type of reaction is this? So definitely it will be an exothermic reaction. There's more energy that is released than is absorbed in this case. So therefore, we know that it's an exothermic reaction. So they are asking in 7.1, is this reaction exothermic or, endothermic or exothermic? Our answer is definitely going to be exothermic. And they want us to give a reason for this answer. So we can say the energy of the products, okay, is less than the energy of the reactants. All right. Or you can say that our delta H, right, which is obviously going to be products, the value of the products minus that of the reactants will actually be negative. So our delta H value will be less than 0. Okay, right. Now they say to us, use energy values A, B, and C, right, indicated on the graph, and write down an expression for each of the following. Right, so they want to know the energy or the energy of the activated complex. So remember, there's our activated complex there, right at the top. So the energy of the activated complex, that would be A. So that's the symbol that we're going to use there. They say the activation energy of the forward reaction. Now, please note, for the forward reaction, we start on the reactants, right? And where do we go? All the way to our activated complex. So that means for the forward reaction, it will be A minus B, right? So it will be the energy of the the activated energy, right? Activated complex rather, minus the energy of our reactants. So which means that would be A minus B. All right. And now they want to know delta H for the reverse reaction. So note, now for the reverse reaction, it means that what would have been your products now become your reactants, right? And what would be your reactants now becomes your products. Remember, when you're talking about the reverse reaction, we are now reversing what we are doing there. So these two react to form the ones that are on the left-hand side, right? So now, which means these are our reactants over here, and these are our products over there. And remember, what do we do when we calculate delta H? We always say product, right? Energy of the products minus the energy of the reactants. So in this case, which means that we're going to have B minus C. So that will be B minus C. Remember, if it was the forward reaction that we are talking about, right? Remember, for the forward reaction, that means these are our products and those are our reactants, right? So in that case, what would have been our delta H value? That would have been products, so that's C minus the value at B. Right, I hope this makes sense, ladies and gents. Right, now let's conclude our question. They say to us, calculate the amount of energy released during the reaction if 0.18 moles, right, of barium hydroxide reacts completely with the acid. Now, I want us to please note the following. Remember that whenever we are talking about the process of a reaction, right? So here it is, they've given us the moles, right? And we know they want to know the amount of energy that is released during the reaction, right? So what do we note? We note that the potential energy is in terms of kilojoules per mole. So that means that the amount of energy, so I'm going to just change the color there, right? So the amount of energy that we have, right? So energy will be equal to 0.8 moles, 0.18 moles, right, multiplied by the number, the delta H value, right? That's 116 kilojoules per mole. So that means I am going to say, well, multiplied by 116 kilojoules per mole. My delta H value was given there. So this is 1 kilojoules per mole. Note that per mole means that if I multiply by mole, I'll only get kilojoules. So what would be the amount of energy there? All I'm simply going to do is just multiply the two together, 0.18 multiplied by 116, and that gives me 20.88 kilojoules, right? Otherwise, you can also, just have that in joules. So that would be 20,880 joules. All right, so that would be 20.88 kilojoules. Now remember, kilo is 1,000, okay? So you could have actually just said 0.18 multiplied by 116,000, okay? Which is actually the answer that we have over there. So this is the amount of energy that would be released, all right, per mole of barium hydroxide that we've got over there. Right, now ladies and gents, that is how the cookie crumbles, right? What I'm going to do is just try to have another question, all right, so that we see that there's really not much to this section. Once you understand, you are set, you are good. All right, let's go to another question. So they say to us, methane is used as an alternative fuel, right? The combustion of methane releases carbon dioxide and water. The balanced equation for this reaction is as indicated there. They say the activation energy for this reaction is 172 kilojoules per mole. Now, firstly, ladies and gents, I want you to note that during the course of this reaction, what happens? Energy is actually released, right? So that means that as we form carbon dioxide and water, we are also, in this case, just releasing energy, right? And look at that. The amount of energy that is released is way greater than the activation energy, the amount of energy that is absorbed over there, right? So if we were to draw the energy profile, okay, and let me do that. If we were to draw the energy profile of this reaction, right, even if we didn't know what the energy profile of the reactants are, right? So let's just say here are our reactants. They've got a certain amount of potential energy. Remember, we always draw this against reaction coordinates or the course of the reaction. Coordinates. This is not against time, ladies and gents, right? And this is our potential energy graph. Okay, we're just going to get to the questions in just a little while. So that means this is what we're going to have. This is the energy of the reactants. Right, note this. Very little energy is absorbed, right? So that means to get to that activation energy at the top there, this would be in this case. So whatever the activated complex is minus the energy of the products, of the reactants rather. So these are our reactants. And this would be the product over there, right? So the activation energy, let me call it EAF, right, for the forward reaction. So the activation energy for our forward reaction is what is given to us there as 172 kilojoules per mole, right? So that's per mole. And what do you notice? There's more energy that is released. So I note there that upon the reaction being formed, products being formed, the amount of energy that is released over there would be 891 kilojoules. So which means this would be 891 kilojoules per mole, right? Now, guys, I want you to really see this. So in this case, what would therefore be delta H? Notice, if they asked us to calculate delta H for this reaction, that would be the amount of energy that is released, right? So that amount of energy that is released minus that activation energy, right? So that means that I would actually say that's, if we are going to add the two together, or rather subtract them from each other, remember that is energy that is lost in this case, right? That is released, so that would be negative 891. Why? Because you are losing it in the system, right? So that would be minus 891 kilojoules per mole, okay? Plus, in this case, we absorbed 172 kilojoules per mole. And so if we wanted to get delta H, that will be the difference between the two, right? So that's 891, or negative 891 plus 172. And we get minus 719 kilojoules per mole. I'm just showing you all of this, ladies and gents, as just in case you would need it, right? Now, just another thing that I perhaps should have mentioned earlier. What happens when you add a catalyst into your reaction? So the moment you add a catalyst, what's going to happen is, right, so your reaction would actually have a lower activation energy, and we discussed this a little bit more in grade 12, right? So your activation energy for the reaction, right, would actually be lower, right? And in this case, your activation energy would actually be lower. Now let's answer the questions that were really asked, right? They say, is this reaction endothermic or exothermic? Give a reason for the answer. Now note, what type of a reaction is this? Again, it is exothermic, right? Why? Right? So the energy that is released, okay, the energy of the products, okay, would be way less than the energy of the reactants. All right, or you can say in this case, the energy that is absorbed, in fact, I think this would be more accurate since that's what you note there. So the energy absorbed would actually be less than the energy released. Okay, and that is how the cookie crumbles, right? They say, explain why all chemical reactions need activation energy, right? So remember that activation energy is the minimum energy required. So this is the minimum energy required for a reaction to take place, right? So minimum energy that is required for a reaction to actually take place. Now I want you to note in this case, right? So the minimum energy required, why do we need it? We said this earlier, so that we are able to break bonds, right? All right, so that the bonds, let's call them, so that reaction bonds are broken. Okay, and there we go. Right, so in this case, that is why we would need the activation energy. And finally, they say, why is this reaction not considered to be environmentally friendly? Okay, so what I noticed there is that it releases carbon dioxide, right, which is a greenhouse gas. Okay, so it releases Well, look at my spelling. It releases carbon dioxide, which is hazardous to the ozone layer, right? Remember that carbon dioxide is a greenhouse gas and it does deplete the ozone layer, right? Of course, if the ozone layer is depleted, you don't need to explain all of that. If the ozone layer, ladies and gents, is depleted, or in this case gets thinner and thinner, the more the ultraviolet rays of the sun will actually become more dangerous. Okay, yeah, so, and that's why we are experiencing all of this global warming, the change in the weather patterns, right? Ladies and gents, I want to leave this here. I hope that I was able to answer all the questions that you need in terms of this section. It really isn't such a bad section. I hope that you guys have been able to understand and follow on. We'll do some more questions perhaps sometime later, but I think that's all you need to know in terms of energy and chemical reactions. Otherwise, from me for now, I'll see you guys again next time. And please don't forget to subscribe and like. Do share with all of your friends. I'll see you guys another time again. Sharp, sharp.